We're now ready for part 2 of this week's discussion. For part 2, we're going to talk about the chi-squared two-way test for independence. So what is the chi-squared two-way test for independence? Well, it examines contingency tables based on a random sample of data from a population to determine if the rows and columns, the different levels of two categorical variables, if they're independent or dependent. So the basic idea is you use it when you have two categorical variables. The data have been gathered from a random sample from a population, and you want to examine whether or not these two variables are related or not. Are they independent or dependent? The test statistic for the two-way test for independence, it's calculated in basically the same way as the one-way chi-square test. However, the expected cell counts, as well as the degrees of freedom, are calculated differently. That's simply because we have two ways, right? So the one-way chi-square test, when you talk about one way, we have one factor, we have one categorical variable with different levels, different categories for that particular categorical variable. For the two-way test for independence, we have two categorical variables, or equivalently, we have two factors, each with their own different levels. That's where the difference between one-way and two-way comes from. But they're both based on this idea of comparing expected versus observed cell counts. So let's look at this example of religious affiliation again, but now we're going to use this variable of gender. So we're again analyzing the religious views of young adults, 18 to 35, and we want to know if there's a gender difference in religious affiliation. Do men and women differ in terms of their religious identification? So this is a real data set, it's a random sample from the population, and it's based on a contingency table of counts from a random sample. This is the data set. Again, we have a set number of rows. We have 518 observations, or people. And then our variables are really gender and religion. So for the chi-squared two-way test for independence, you're working with two categorical variables, or two factors as they are sometimes called. So let's look at the basic table of counts. This is just a frequency table. Right? A frequency table of counts gives us an idea of the overall sort of joint distribution for religion and gender. So you can see that there are 143 women who identify as Protestant, 104 men who identify as Protestant, and so on and so forth. In terms of notation, we use R to refer to the rows of this table, and we use C to refer to the columns. Typically, we put R before C. So you might say, oh, we have a 2 by 3 table, right? Or R times C table. What that is referring to is the fact that we have two rows, R equals 2, and we have C equals 3 columns. The total sample size is simply, you can just add up all these different cells, that's 518. So 143 plus 104 plus 76 plus 56 plus 64 plus 75. Add those counts up, you get 518. The question we want to answer is, are these two variables related? Is gender and is religious affiliation, are they independent or dependent from each other? An important point is that if we had the population, if we had a census, if we had all young people in the United States and knew their religious affiliations, right, we could just work with the table itself, right, with the data itself in the population. But because we don't have access to the population, we need to conduct this chi-squared two-way test for independence. It's a statistical inference test. Right? Again, the idea is we want to use a sample on hand to make an inference about the population. Right? We want to know in the population, are these two categorical variables independent or dependent? So there are a couple steps for conducting this hypothesis test. Preliminaries, you state the target population, the parameters of interest, and you check the required conditions. Then we go through the null and alternative hypotheses. You select the significance level. You compute the chi-square test statistic, which is quite similar to the one-way test, but there are some differences. But the basic idea holds that more extreme that chi-square test statistic, right, the more inconsistent our data is with the null hypothesis. Then what you do is you assume the null is true, and then you make a decision by comparing that chi-square test statistic with a critical value that lies on the chi-square distribution model with a certain degrees of freedom. And you can also compare or compute the p-value. Right? Then you finally state your conclusion. There are a couple requirements for the two-way chi-square test for independence. First of all, the data should be randomly selected from a population. That's because this is an inferential test, again. Right? If you had the population, you could just look at the data itself. But since we don't, we're using this random sample to say, do we think in the population, these two categorical variables are independent or dependent? The sample data, it should consist of counts or frequencies from a contingency table with R rows and C columns. All that's saying is that the data should entail categorical variables of counts from a contingency table with two variables. For each cell in the contingency table, right, the expected cell count should be at least 5. Again, the expected cell count, it's the number of observations, the number of people that would exist if the two categorical variables are in fact independent in the population. It's not the observed cell counts. Right? There's no requirement at all that the observed cell counts, the counts from our data for each cell must be at least 5. Let's go through some of the steps for conducting this hypothesis test. First of all, you state the hypotheses. For a contingency table that has R rows and C columns, the two-way chi-square test for independence, it has the following null and alternative hypotheses. The null is simply that in the population, these two categorical variables are unrelated. They're independent. Again, you can think of the null as saying nothing's going on. If gender and religious affiliation, they're not really related in the population, well, then you can kind of say nothing's really going on. The alternative is that they are in fact related. They are dependent. For step 2, we choose a significance level. We're going to use alpha, right, just by convention. For step 3, we can compute the test statistic. The test statistic for the chi-square two-way test for independence is simply as follows, where k is the number of cells and each cell is indexed by I. Now keep in mind, since we have two variables, the number of cells is 2 times 3 because we have 6 cells in our contingency table. But the basic mechanics, the formula is actually in fact the same. All you're doing is you're taking the observed minus the observed counts for each cell, squaring it so it's positive, standardizing it by dividing by the expected cell counts for that particular cell, and you're adding it up for each cell. So k is in fact the number of cells. As before, the more extreme the chi-square test statistic, the more inconsistent the data is with our null hypothesis. Right? The test statistic, it's again similar, except again we're using expected cell counts. Right? So we have 6 cell counts. How do we calculate the expected cell counts? Well, you first need to obtain the expected cell counts under the assumption of the null hypothesis. This is how you calculate the expected cell counts. Right? The null is simply that these two variables are independent. So you take the row total times the column total divided by the overall total of counts. These are simply obtained from the contingency table itself. And we'll go through an example so you can see that. Then what you do is once you calculate these expected counts, right, you can compute the test statistic and compare it with the critical value. Again, if the chi-square test statistic is greater than or equal to our critical value, which is based on our level of alpha, as well as the sort of form of the chi-square distribution model, meaning the effective degrees of freedom, then we reject the null of independence in the population. Right? We will use statistical software typically to find these critical values that lie in the chi-square distribution. So the critical value, it depends on alpha, but it also depends on the degrees of freedom, as I just mentioned. The degrees of freedom in the case of the two-way chi-square test for independence, it's a function of the number of rows minus 1 times the number of columns minus 1. And again, we have this technical note because the chi-square distribution model is from 0 to infinity. It's technically the chi-square test, it's based on a two-sided alternative, but the rejection region is only in the right-hand tail. Again, this is because if an observed cell count is either above or below the expected cell count, they both will lead to a large calculation in the chi-squared statistic, meaning that chi-square test statistic will be pushed towards that right tail. Then you can also make a decision by calculating a probability or p-value. For the chi-square test, again, the p-value is simply the probability of obtaining a chi-square test statistic greater than or equal to the one we actually obtained. So based on this probability value, we can just compare it with alpha. Right? We typically will use statistical software to calculate our p-value. Again, we have this technical note. The chi-square test, it's a two-sided alternative, but the rejection region, it's based on the right-hand tail. So the p-value is based on only in that right tail. That's because the chi-square distribution model ranges from 0 to infinity. For step 5, we can make a conclusion. So we make a decision to either reject the null or fail to reject the null based on the previous step, step 4, either step 4a or step 4b. If you reject the null using either the critical value or the p-value, then you can conclude that the two categorical variables are in fact dependent in the population. This suggests that they are in fact associated or related. They're not independent. If you fail to reject the null, then you can conclude that the two categorical variables are in fact independent in the population. They are not associated, they are not related. That's because our null is in fact that they are independent of each other.